I am Giulla Galli from University of California, Davis, and I'll be telling you this morning about molecular dynamics, and in particular the goal of this lecture is to get at the end of the lecture to tell you what ab initio molecular dynamics is. So the picture that I put here in the background, this yellow, white, and kind of blue blobs, is a little bit representative of systems that we may be interested in looking at with molecular dynamics. So the white and yellow spheres represent atomic position in a disordered system, a liquid. And the blue blobs represent charge densities. So this is a system that you may be interested in studying by using molecular dynamics, and by using in particular ab initio molecular dynamics that gives you access also not only to the atomic structure of the system, but also to the electronic properties of the system. So what I will do this morning is tell you about molecular dynamics. So I'll start it from the very beginning. What is molecular dynamics? We'll discuss this a little bit. And then I'll go through the ingredients that one needs to know in order to be able to perform a molecular dynamics simulations. And then give you just an idea of some of the properties that one can access by doing molecular dynamics. And then finally, I'll talk about doing simulation using forces derived from density functional theory. And this is what I mean when I say ab initio molecular dynamics. So it would be good, actually, if we could go through this lecture in as much an interactive mode as we can. So if you have questions, please interrupt me anytime. If there are no questions ever during the morning, I'll try to ask questions so that we interact, and also we have a discussion. So are there any questions about this plan or whatever you may want to ask before actually I start the lecture? Any curiosity, anything? No? Okay, all right. All right, so are there people here who are familiar already with ab initio molecular dynamics, who have been doing ab initio molecular dynamics simulation? You are? Okay. So some people are, so you have been doing this kind, and people have been doing classical molecular dynamics? Okay. All right. So at the beginning, for those people, I may say things actually that are quite probably obvious and straightforward, but I am planning to start from the basic definitions, just to be sure that everybody here is on the same page. Okay, so we look at a classical system of interacting atoms, ions, and what we want to do is solve numerically the equation of motion of the system, and the equation of motion are just given by Newton's second law, so F equal ma, and in order to know the forces acting on all the atoms of my system, of course I need to know the interatomic potential. And molecular dynamics is a technique to solve the Newton equation of motion and to determine the trajectory of my fully classical system at this point as a function of time. If I integrate numerically the Newton equation of motion and I get the trajectory of my system, then I can obtain properties of the system as time averages. And molecular dynamics is a deterministic method in the sense that the state of the system at any future time can be predicted from its current state. And when we do molecular dynamics, we use numerical techniques to integrate these equations by finite differences. So we compute at a certain time forces on atoms, and then we determine position and velocities. And then we move the system by a very short time step, and we recompute forces and position, and in this way we evolve the system. Once you have the interatomic potential, it is a pretty straightforward, at least in principle, way to go. I mean, we have a pretty straightforward way to go about solving these equations. Now, the reason why actually computing time averages to obtain thermodynamic property of the system worked is because under the hypothesis of an ergodic system, so we always work under the hypothesis that we are looking at an ergodic system. Under the hypothesis of a thermodynamic system, once the interatomic potential is specified, we can identify temporal averages with statistical averages, right? So in molecular dynamics, we integrate the Newton equation of motion with finite differences over time. We determine trajectories, and then we take temporal averages, written here for a generic properties represented by the variable A. And under their ergodic hypothesis, and for long enough simulation time, of course we will discuss what long enough simulation times means, and for long enough simulation time, for simulation times going to infinity, we can actually identify the thermodynamic averages over a certain ensemble, statistical ensemble, represented by a density rho here with the temporal averages. So again, here is our basic assumption, and as I said, we will have to discuss, and I will present example, what actually having simulated for enough time means, and this has usually a different meaning depending on the system, but also depending on the properties that one may want to simulate. So, yes, please.
Can you explain a little bit what is ergodic hypothesis?
Yeah, so that if you actually, during your molecular dynamic simulation, in order for the system to be ergodic, the system needed to explore with equal probability all the portion of phase space. It doesn't need to be stuck in any part of phase space. Actually, this hypothesis is an hypothesis that even if it's actually satisfied in principle, one needs to check always once a technique to solve the equation actually has been chosen. And I'll get back to that. For example, there are, even if your system is in principle an ergodic system, there are techniques that one may choose, for example, to keep the temperature of the system constant at some point, that may lead to the system being stuck in certain part of space, in phase space, and so the model system that you are simulating not be ergodic anymore. So this is actually an important thing to check, and this is not always done, actually. So this is probably, so the molecular dynamics, really the technique was invented pretty much exactly 50 years ago. And this is the seminal, there are several seminal papers actually. I've listed them here if you're interested to have a look. They are given here starting, actually the very, very first one is 57, but I think that this paper by Bernie Alder and Wainwright is considered really the paper where molecular dynamics has been invented, and it is a study of liquids and solids. They are represented with 32 atoms and with the hard sphere potential. I strongly recommend everybody to read this paper to understand how many new concepts actually can be contained and how much vision of a new field can be contained in one single paper. This is absolutely an amazing paper written 50 years ago. And it's interesting actually that the authors say here at some point, let me, Sarah. Oh, the study of this many-body problem is carried out by an electronic computer. They still bother, right, to specify that they are using actually an electronic computer. Really, I mean, read the paper. The applicability of the method to the solution of many-body problem in both equilibrium and non-equilibrium statistical mechanics is discussed. I mean, there are a lot of concepts and a lot of things that people have developed over 50 years already contained in this paper. And the other paper, which is considered as the beginning really of the field, is the paper by Ernest Rahman at Argonne, and using a CDC computer. This is a picture actually of the CDC in 1963. This is 1964. And here already the number of particles 5 years later on a digital computer that they were looking at is much bigger, 864 particles. It's a Lennard-Jones potential. I'll come to that in a second. And already many properties are computed. These are amazing papers, and I again suggest, I recommend that you have a look at them. Actually, if you go back to this paper really and you see how many concepts, probably today for all the concepts in this paper you would write like 5 PRLs or something, and this is just a Journal of Chemical Physics paper with everything in it. It's quite amazing. Okay, so this is the definition of molecular dynamics, and now let's go through all the ingredients that one needs to know to perform a molecular dynamics simulation. As usual, right, in a simulation, we need to define a model, okay, representing the real system, and then we do the calculation of the model. This, in a way, it's always true also for all the systems that you have seen, of course, last week, and in general when you do electronic structure calculation. But it's particularly true when you do a molecular dynamics, and I will tell you what I mean when we talk about liquids and disorderous system. You actually have to make many choices to define the model system that you simulate. Okay, so how do we perform a molecular dynamics simulation? First of all, we have either to determine or to compute on the fly the interatomic potential, right? We need to compute forces and we need to know the interatomic potential. Then we have to choose the number of particles in our simulation cell, the size of the simulation cell, and this is part of the definition of our model. Then once we have defined the model system, which is the potential and the size of the simulation cell, we need to choose the algorithm to solve numerically the Newton equation of motion. And then we need to choose the statistical ensemble that we want to sample. Whether we want to do a micro-canonical simulation, meaning we just want to simulate a system which is isolated and for which the total energy of the system is conserved. And usually you see a microcanonical simulation called NVE, N number of particles, constant number of particles, constant volume, constant energy, or constant temperature, which may mean, if you choose the right algorithm, that you are sampling the canonical ensemble, NVT, or, for example, constant pressure and constant temperature, NPT. Okay? So what I'd like to do is take each of these choices that we have to make to perform a molecular dynamic simulation and discuss them one at a time, and to get to a point where we actually are ready to perform a molecular dynamic simulation and to interpret the result coming out from a simulation. Please.
So is there a reason why there's the grand canonical ensemble is not on the list?
Yes, there is a very good question. Yes, there is a very good reason. And the reason being that it is a very difficult, within a molecular dynamic simulation, it has done within a Monte Carlo framework, it is very difficult to actually come up with a framework where you change the number of particles of your system. This is very difficult. It has been done within a Monte Carlo simulations, and there is one reason is that you don't compute forces actually in Monte Carlo simulations, so you don't have all of the problems that you would have in molecular dynamics in assuring the continuity of your potential energy sources and so on and so forth. Actually, I am not completely sure, but I know that there have been recently some attempts actually to do grand canonical simulations, but I don't know what the state of the art there. I know that you can do grand canonical simulation actually in a quite good way by using Monte Carlo, but basically molecular dynamics there is almost nothing. So it's a very good reason.
In fact, I have the same question. I'm asking that how about like the canonical ensemble? No.
So the change in number of particles.
No, I think the grand canonical ensemble is that the total number of particles is changed.
Yeah.
How about the canonical ensemble?
Oh, the canonical ensemble. So the reason why I wrote here constant temperature instead of writing canonical ensemble is a reason which will become clear in a minute. So certainly you can, let me put it this way and I'll get back to that. There are ways of keeping the temperature of your system constant that actually are designed to sample the canonical density in phase space, and so to sample the canonical ensemble. There are also many other techniques, and I'll mention them, to keep the temperature constant of your system that actually do not sample the canonical distribution and do not sample the canonical ensemble. Nevertheless, they are used, and of course you need to use them with care, and especially they are used to bring your system towards a situation of equilibrium that then you sample by using the proper canonical distribution.
Okay.
So this is this actually constant temperature does contain the canonical ensemble, and you can do it quite easily. Well, much more easily than a grand canonical simulation, to put it this way. Yep. Other questions? Okay. So let me just tell you a few words about the choice of an interaction potential to start with. So let me also remind you of two things which, again, are very general. They are not only appropriate to discuss when we discuss molecular dynamics, but I really want to make sure that we all understand this. No matter what you do, no matter how sophisticated the method that you choose to describe the interatomic potential, your interatomic potential is always approximate, always, okay? So you have to keep this in mind, and of course you have to have in mind that the validation of your simulation is a key step in any simulation that you can possibly do. And this, of course, is also true when you do any electronic structure calculation. Your electronic structure calculation is always approximate. There are no exact results, and we have always to have this in mind. Okay, so there are basically two routes that one follows. First one is to use empirical potentials. And the word empirical here says that one comes up with a parametric form, a functional form of the potential, and then there are parameters in this functional form, and you adjust the parameter by fitting by fitting basically experimental data. For example, you may fit the results of scattering experiments, like if you have neutron, say you want to simulate a disordered system, you have data coming from neutron scattering or X-ray scattering experiment, you may fit those. Very often thermodynamic quantities are fitted, including specific heat, compressibility, and so on and so forth. Or you actually can just fit any kind of experimental results you deem appropriate. Of course, then there is a problem of testing whether your potential can also describe thermodynamic conditions representing states that have not been fitted, right? These may not actually quite work. And the one, of course, typical potential that have been used in many cases is a sum of pairwise interactions. The other class of potential are those which are ab initio derived. And there are two very different things that you can do. One is, again, choose a parametric form, same as here, but instead of fitting your potential to experimental results, you fit your potential to the results of first principle calculations that may be density functional theory or quantum chemistry methods. Okay? So same spirit. Your potential has a certain form with certain parameters, but here you get your parameters from experiments, and here you get your parameters from calculations. So this is a ab initio derived potential in the same spirit as the empirical potential. Or, and this is where we actually want to get at the end of this lecture this morning, you compute the many-body interatomic potential at each set of the atomic position in your molecular dynamics. So you have a set of position you start from, you move your system by a small time step, you recompute from, for example, by using density functional theory, and this is where I want to get to, your potential at each step. The potential is not fitted to anything, it's recomputed at each step. So you see, philosophically and in practice also, these are two very different approaches, even if in some cases their accuracy can be actually quite similar. Okay? So in this talk, and what I mean by ab initio molecular dynamics is a molecular dynamics where the potential is derived from DFT forces and is computed at each step. In the quantum chemical literature, sometimes ab initio molecular dynamics is also used to actually describe this other approach. So depending on, and if you read the physics literature, ab initio molecular dynamics is always describing this approach. The quantum chemistry literature sometimes uses this ab initio molecular dynamics also to describe the approach of fitting a detection. Okay. I will not go through a description of, yes, please.
What are the sizes of the systems that you can do with the quantum chemistry type technique? Is it essentially the same as a classical MD?
Well, that's a good question and also kind of a difficult one. So your question is, what are the sizes that you can actually deal with here once the potential has been derived, right? Not including the complexity of the calculation that it takes to do. Basically, at that point, you can. So the size that you can deal with at that point is determined by the range of your potential. So if you derive a potential which is like as short range as a Leonard-Jones potential, or as short range as, say, a Tresor potential that I mentioned in a minute for silicon, then you can do exactly the same calculation that you do with an empirical potential. It also depends whether, for example, you have to deal with Ewald sum in your simulation because you have dipolar interaction and so on and so forth. But let aside the complexity that enters in the derivation of this, once you have determined your potential, the complexity, the number of particles is determined by the range of the potential, how long range it is, and how many neighbors you have to include in your neighbor list, and so on and so forth, and how long it takes to compute the interaction. Exactly the same way as here. But of course, it is usually, I would say, probably always, well, in most cases, much easier to fit a bunch of experimental results than actually to do all the calculation that it takes to derive this potential. That's, yes?
What about the transferability when you do that?
Yeah, the transferability is really at this point, once you have a potential, the key question. I will actually show you an example later on for water, a very, since also we talked about water yesterday, about the transferability of potentials derived by fitting quantum chemical calculation of dimers to actually simulate liquid water. Very recent paper that appeared in Science 1.5 years ago. Transferability, I don't have a general answer to this question. It depends on the system, and it's very difficult to answer. For example, water is typically a very difficult problem to have a good transferability. If you want to describe liquid water and then ice, and you want to do so by actually using fitted quantum chemical potential just derived from a computing interaction between water clusters, it's extremely difficult because the range of the interaction decays very, very slowly, and it's extremely difficult to actually get it from a bunch of calculation of clusters. But I'm sure that there are systems where one may find actually a better transferability. Certainly there are cases where the transferability is a huge issue and it's difficult to deal with.
In the second case, do you get to choose which form of the potential you want to use?
No. In the second case, and this is what I will be talking about and what we are aiming at this morning, really what you do is you have, and I will explain this in more detail at the end of the lecture, you actually do a density functional theory calculation within, for example, NDA or GGA, or choosing the functional that we have been discussed last week or yesterday. You do a density functional theory calculation, you find the total energy of your system for given atomic position, you compute the forces using the Hellman-Feynman theorem, and then you use the forces to move your atom. You generate a new set of atomic position, and you redo a density functional theory calculation, and you redetermine the forces. And there are ways to make this process of redoing the calculation fast, and we'll talk about this, but there is no assumption whatsoever about any parametric form of the potential.
Excuse me?
Yes?
How the computational cost increases if you, along with the binary interaction, if you also calculate three-body and slightly higher body interaction?
Oh, so you mean in your molecular dynamics simulation? Well, actually, okay, let me, I have an example here of, just hold on 1 second, and then I'll get to that. So I wanted just to give an example. I'll go very quickly. I don't want to give you examples of all the possible empirical potential. There are zillions, and they depend on the system. And I wanted to mention 2 cases. One is one potential that is one of the probably most used, is the Lennard-Jones potential. A very, very simple interaction, pairwise interaction, actually with this form, 1 over r to the 12th minus 1 over r to the 6th, with 2 adjustable parameters, one with a length dimension and the other with an energy. And this is a plot of the potential as a function of the separation and of the force. And so if you actually, as I said, these are length and these are energy unit, and the mass unit is simply the mass of the particle, and you can also get rid of it and actually incorporate this in the time step for one component system. The reason why I mentioned this potential is because it's one of the first potential that has been derived and used, and it is still very, very much used, for example, in its form, and also sometimes in its original form, when there are organic system or kind of biological system, for example, involved, and also to describe van der Waals interaction. There are forms fitted of potential these days, for example, that are even added on top of density functional theory calculation that are based on the form of Lennard-Jones potential. And this is a two-body potential. Now, another example of totally different that I want to just mention is the example of the empirical potential for silicon. Just to give you an idea of what people do for empirical potentials. And these are three forms of empirical potentials that have been developed in the literature, and they are very much used. One is a Stillinger and Weber potential. And so to get back to your question, there are pairwise interaction and three-body terms. And this is a Tursoff potential. And I've written down here the expression, not for you to read and go on, over this in detail, but just to give you an idea, this is the sum of pairwise interaction. And then there is a functional form here, which is specified and chosen, and there are parameters. Actually, overall within a complex algebraic form, and all, if you read this later on and you see all the parameters that are there, these are all the parameters that are used to fit to experiment. So how much more expensive it is to use three-body terms and pairwise interaction? Well, there is a complexity related to the range of the potential again, and how far out you have to go to, for example, compute neighbors list. But really, the time that it takes, it depends how expensive numerically it is to evaluate these three-body terms. For example, here, the Stillinger-Weber has three-body terms, which are much simpler to evaluate, just because of the assumption that it has been made, than the three-body terms that are here in this environmentally dependent interatomic potential developed by the Katsiras group about 10 years ago for silicon. So there are always three-body terms here and here, but here they are environmentally dependent, meaning that every time that the neighbors of a certain atom change, you have to recompute actually even some integrals that determine certain parameters entering here. Here, the three-body terms are set once and for all, and they are much easier in the case of the Stillinger and the Weber. So, short answer is, like often in molecular dynamics, for potential it depends on the system, and two main things. It depends on the range of the potential, and it depends on whether you have to recompute your parameters depending on the environment or not. And this is, so I've chosen silicon just because, of course, it's such an important material, and also because these three potentials that have been developed and used, they are still used today for a lot of interesting problems in material science. And for different systems, all of these three potentials have been very successful, although not all of them have the same transferability properties, for example. Okay, other questions on potential? Okay, so let's hold on now. So I here, this was just to give you an idea of what one does to choose the potential, and then we'll get back to this part at the very end of the class this morning. and I will tell you then what to do to actually compute the potential at each step when we do molecular dynamics. Let's go on now to discuss what we need to choose when we want to perform molecular dynamic simulation. So we have decided which potential we use. Either we compute it or we fit it or whatever, and we have an interaction potential. Now we have to choose the number of particles or the size of the simulation cell. And how do we do that? This also is a non-trivial operation. First of all, we want to avoid, when we do a simulation of a bulk system, so you want to simulate a piece of silicon, we want to simulate liquid water, or you want to simulate a very complex nanostructural materials of all sorts, and you want to know the bulk property of this material. You want to avoid surface effects, and you want to include in your cell all the relevant bonds and correlation in your system. If you have a periodic solid, this is pretty simple, right? As long as you do not have defects in your solid, of course. If you have a liquid, deciding how big the cell is to actually include all relevant bonds in your exogenous system is a non-trivial, actually, thing to do. And we'll see a couple of examples later on, and I'll get back to that. So how do we avoid surface effect? We avoid surface effect by using periodic boundary conditions. What does it mean here? Very small empty cell, 3 particles. What we do is that when the molecule, if we are simulating a molecular system, or when an atom, if we are simulating, when an atom or molecule actually go through the boundary, then we have its image going back in through the opposite boundary. So we always simulate the same number of particles, and we apply periodic boundary condition so as to have to completely avoid surface effects. And we use what is called the minimum image convention to account for neighbors. So we have to actually have a way to tell that a particle, actually, when it gets to the boundary, how it interacts with its periodic image on the other side, right? Now, when we compute so-called neighbors list in a molecular dynamic simulation to count the number of neighbors of a given particle, taking into account that we have periodic boundary condition, if we want to simulate a very large system, we usually also need to be careful about the scaling of the algorithm that we choose to compute neighbors list, right? Because there are, if you just do a neighbor list in a straightforward way, you end up with a sorting algorithm, and which scales like the square of a number of particles, and depending on how many particles in your system you have, the scaling may be unfavorable, and there are algorithms that have been developed for large-scale simulation that are actually linear scaling to account for neighbors list. Okay, so we have the potential. We apply periodic boundary condition, and then we need to assign initial configuration of for our system, right? We have to start. We are solving Newton equation of motion, second order differential equation. So we need to assign the initial coordinate and the initial velocities. So how do we assign initial coordinates? Well, sometimes it's a trivial choice. Say you want to actually start from a crystalline solid and you want to melt it. You know the crystalline position. You know exactly what to do. In some other cases, you don't know what to do. You may actually choose input from experiment, or you could randomly choose the position of your particles, but usually this is not recommended. It actually can create quite a bit of instability, or actually lead to a situation where it is not that trivial to reach equilibrium. And then you assign initial velocity. So the velocity, we are dealing with a purely classical system. So the velocities are related to the temperature of the system in a very simple way. So the kinetic energy of the system is, of course, given by 1/2 mass velocity squares, and the temperature is related to the velocities by this relationship that we all know, 3R and kVt, and n is the number of particles in the system. So at thermal equilibrium, the expected value of the kinetic energy is this, and so we can derive the temperature of the system from the velocities. And one way to assign initial velocity, for example, is assigning velocity components from a random Gaussian distribution with mean at 0 and with this type of standard deviation. This is one way. There are many different. You can assign random velocities if you're not very worried about reaching equipartition of energy. So usually in a molecular dynamics simulation, you are actually worried on how to take your system from the initial configuration to equilibrium. And by equilibrium, we mean a situation where you have equipartition of energy in each degree of freedom of the system. If you actually start with velocities such that the initial equipartition of energy is very bad, it may take you a very long time to get to equilibrium. So this is, of course, the initial conditions are not the only, by no means, the only condition that determines how long it takes to get to equilibrium, but it's one of those. And so one usually is careful.
I have a question. See, if you have a quadratic potential, like from the binary interaction to generate, whatever initial condition you choose, is it not guaranteed that quadratic potential and quadratic kinetic energy will lead you to equipartition if you do not have any phase transition, isn't it? What do you mean by bad initial or good initial condition?
Well,
because whatever initial condition I start with, in the binary interactions, in the quadratic nature of the kinetic and potential energy, that is already embedded.
No, well, suppose that actually you have a you have a system where there are two parts of your system described by whatever potential that you want that have vibrational modes or vibrational spectra, I should say, that need not overlap at all, or that have a very small overlap. It will be very difficult to bring your system to equilibrium and to have equipartition of energy and to have energy equally distributed in each mode. And suppose that you choose your initial condition in such a way that only the modes of one part of the system, for example, you have light and heavy particles are excited, then it will take a very long time for the energy to flow also to the other part of the system and to actually get equipartition of energy. How fast this process actually happens is also determined by the way that you choose actually to heat up your system, the thermostat that you use, and we'll get to that. But the initial condition may actually be one of the, not maybe, but usually are, one of the ingredients that one needs to be careful about because they do determine the speed at which the system reaches equilibrium.
So people usually zero out the linear momentum, but they usually don't zero out the angular momentum part. Is there any special meaning of that?
So the angular momentum is not conserved in an NMB molecular dynamics simulation. So there is no conservation of the total angular momentum actually, and this is it actually quite interesting, because if you do a molecular dynamics simulation, for example, of say a big cluster, right, and you put the cluster in a molecular in a certain in a cell, and you do a molecular dynamics, depending on also on the initial condition, because the angular momentum is not conserved, your cluster may start rotating. I don't know, you may have seen situation like this, and actually you don't quite know what to do with that. I mean, there are ways of correcting that, but it's just not conserved in an MD. That's but if you have a bulk system, this is not a problem. If you have a finite system in your MD cell, yes, this is a problem actually. But P, the linear momentum, is conserved, and actually this is one thing that one usually checks, that the total energy, if you do an MVE and you are simulating an isolated system, is constant on average, and the linear momentum as well.
So is that sort of algorithmic problem or numerical problem?
I'm sorry, say it again.
Why does the angular momentum is not conserved? Why is the angular momentum conserved? Is it because of a numerical algorithm to simulate molecules, or?
So I don't think that this doesn't. Go ahead.
I think the question is, if you simulate a finite system in vacuum, it's actually going to be conserved. But when you have periodically repeated system, it's not conserved. I think that's what happens. I mean, the reason the angular momentum is not conserved is the periodicity of the system.
Oh yeah. Sorry,
I mean,
I should have said that.
If you had just a single copy of the system, it would be conserved.
Yeah.
So
Oh yeah, because there is no
what
other
you're describing
way.
is a periodically repeated system.
Sure.
So it's
Yeah.
this one.
So it's because, but you basically there is no way to do molecular dynamics without applying periodic boundary conditions, right?
Well, you could. I mean, classically, you could.
Yeah, you could. I guess you could. Yeah. Actually, at the very, very beginning, you're right. At the very, very beginning, I think that one of the first paper by Anisram, one of the very first MD simulation was not with periodic boundary condition. Yeah, in principle. Other questions? Okay. So, how do we solve the Newton equation of motion? By finite differences, actually, in principle, quite straightforward. We advance the system by a small time step during which we assume that the forces are nearly constant. And so one thing that you could think of doing, and actually it has been done many, many years ago at the beginning of the whole business, is just to do a Taylor series expansion to second order of the atomic position, like so. Here is I'm doing a Taylor series expansion of the atomic position. This is the velocity, this is the acceleration, and this is the same thing for the velocity. Usually, it is never in any molecular dynamic simulation a good idea to compute the derivative of the forces with respect to time, first of all, because this is a very time-consuming operation. It's too costly. It is almost never done. But the point here is that if you actually just straightforwardly do this Taylor expansion, and you use the first equation to compute the position at a time t plus delta from the position and the velocity as the time t, and then you compute the velocity from the new position, you actually obtain an algorithm which is a complete disaster. It is not time reversible, first of all, but also you have a catastrophic energy drift. I mean, if you look at your total energy, which should be oscillating, and you should be on average constant, your total energy completely drifts, and you are not able to integrate your system for more than a few steps. So you need to do something better than that numerically, and this has been done by Verlet. And this is a very old algorithm that everybody uses, and especially this is the algorithm that everybody doing the first principle molecular dynamics uses in the codes these days used to do first principle molecular dynamics. So the Verlet algorithm, it's very simple but extremely powerful, and it is an algorithm correct to the order delta t to the fourth. So what you do you do a series, a Taylor expansion of your atomic position. Sorry, here there is capital R for atomic position, same as before. So small r, it's the same variable. So atomic position, Taylor expansion to find t plus delta t, the position at time t plus delta. Here it is. Velocities, acceleration, derivative of the acceleration. And then you actually do the same thing to find your position at time t minus delta. Same thing. You sum these two equations, all the odd terms cancel out, and you end up with a simple equation to predict the position at a time t plus delta from time t and time t minus delta, which is correct to the order delta t to the fourth. Okay? Very simple, almost trivial, but extremely powerful. And then you can also derive your velocities, and actually you can predict the velocity as time t plus delta from the velocity and the acceleration to the order delta t to the cube. Okay? In many codes, and actually in all of the first principle molecular dynamics codes, where usually we use a very small time step, and I will qualify what very small means. One actually just get the velocity from the predicted position of the atoms, and this is obtained up to the order delta t squared. We don't actually use this expression down here, and this is an expression that is used in many classical molecular dynamics codes. I mean, by classical molecular dynamics, sorry, I mean molecular dynamics code using empirical potential. Okay, so there are a variety of other algorithms, and I'm not going through this algorithm. I'm just writing down names for you in case you see these names in books and you want to know how to go back and understanding this algorithm. One is called leapfrog. It's equivalent to the Verlet algorithm, but one ends up with a slightly different expression for predicting the coordinates and the velocity. And then there are higher order algorithms like Biemann's, order higher than delta t to the fourth. And every time we do ab initio molecular dynamics in all the codes that you will use these days doing ab initio molecular dynamics, we really don't even bother about this again, because we are always, for reasons that will become clear later on, very conservative in the choice of the time step of our molecular dynamics because of our concerns of getting the electronic structure right. And so the Verlet algorithm is perfectly fine. So in all the codes that you will see, the Verlet algorithm is the one always used to integrate the Newton equation of motion. Okay. So as I said, it's a very fast computationally. It doesn't take up very much memory. There is a very good conservation of energy, and it's a time reversible algorithm. And these higher order methods that I just mentioned, without actually going through those, usually require more storage. But you know, when you do a molecular dynamics simulation, even if we wanted to use them, and as I said, we don't really, but if storage wouldn't be our problem, because here we are talking about storage of the ionic position, and the computational limiting fact in ab initio MD is really doing the electronic structure right, and so we can never use very many atoms so as to be really concerned about the storage of the ionic position, right? We do 100, maybe 500 atoms, 500 times 3 or something, and we are never, you know, if we wanted, we could store the atomic position in many times, and this, of course, wouldn't be a problem. We are limited by other things, so we are never really worried about how many velocities or atomic position we have to store when we solve our Newton equation. So how do we choose? So questions here before I go on. So how do we choose the time step? Well, there are no real rules, right? So if the time step is too small, we do not have a good sampling of phase space. And if it's too large, then we actually incur into instabilities in solving our equations. So if you look at the time step that one may want to use, of course they depend on the system, they depend on the temperature, and so on and so forth. They are basically in the range of 0.1 to 10 femtoseconds. In many codes, ab initio molecular dynamics codes, we use atomic units, and we use atomic units also for the time, and 10 atomic units are 0.24 femtoseconds, just to give you an idea. So this is also what you will use time step in atomic units in all the exercises that we will do today and tomorrow. Of course, if you're simulating a liquid, you need to make sure that the time step is small compared to the mean time between collision, and of course this, as I said, depends on the temperature. Now, you find this actually written in many books and also in many papers, that the rule of thumb for choosing your time step, for example, for flexible molecules, is that the time step should be no greater than 1/10 of the time of the shortest period, right? So, for example, if you have a flexible molecule and you look at the vibration, I don't know, you have water, you look at the vibration of the OH stretch, and if you use this rule of thumb, you would say that your time step should be smaller than 1/10 of the time of the shortest period. But, I mean, this rule is not always applicable. And again, if you want to simulate water and if you want to have a good conservation of energy, actually your time step to ensure proper energy conservation needs to be about 1/40, not 1/10. But this is a rule of thumb that you see written in many places. And when you see this rule of thumb, just don't apply it straightforwardly, because actually it's really a vague indication of what the time step should be. And in many cases, it is not valid, strictly valid. So these are just some numbers that I took from this book here. If you have atoms like rare gas atoms, you have time step of, in seconds of the order of 10 to the minus 14. For flexible molecules, maybe you are around 10 to the minus 15 or so. And if you have certain type of bonds, 10 to the minus 15. This is really to give you a vague indication, okay? It depends on the system, it depends on the temperature, and again, for the choice of the time step, there are no rules. The very first thing that one should do when one wants to do a molecular dynamic simulation is carefully test the time step, and this is tested by looking at the conservation of energy, and keep in mind that the time step that you may need to use, of course, does change depending on the temperature, because when you actually heat up your system, then you sample part of the potential energy surface that you do not sample at low temperature, and then your time step actually may need to be different. All right. So we have looked at the interaction potential, simulation cell. I don't know why this is like that, but anyway, the algorithm. And now I want to go on and tell you about the choice of the statistical ensemble. So any question before I do that? So one choice, we already talked about that, right? So just simulate